All right, so hello everyone. Welcome to the tutorial session of state-space approach to control system analysis and design. I am Srishi Siddharth and I'm a TA for sports. So let's begin with writing down the topics that are going to be covered today. Just a second. Okay. So I wanted to give a few comments on the Kalman filter, which was discussed in the previous tutorial session. The solution of the algebraic Riccati equation. Just a second. Yeah. Which is denoted by P is symmetric. Don't have, so the P is actually for a second order system, which is P11, P12, P12, and P2. And we do not have to consider the case when we have a general matrix P. So we have only one case and P is symmetric. We can substitute this into the algebraic Riccati equation and solve for P. That was AP plus PA transpose minus PC transpose R inverse E plus PA. And then find out the values of P11, P12. Then we'll talk about the case study of the nuclear reactor, modeling of the nuclear reactor. So this is we are going to study the nonlinear model. Linearized model. After obtaining the linearized model, we'll discuss linear output feedback control. Alright, so we'll begin with a short example on the continuous time Kalman filter so that I can uh, explain the solution of the algebraic part equation, and then we'll move on to the case study of the nuclear reactor. This is continuous time Kalman filter design. So I write down the question. It's a second order system. system is x dot equals 0, 1, 1, 0, x plus 1, 0, u. So the input is present in the dynamics of the first state, and we have the associated input noise, W. So the variables x, u, and w are functions of time. And then we have y equals 1, 0, x plus w2. This is the output noise. So where w1 and w2 are uncorrelated, white noise processes the covariance matrix is also known as intensity. So with intensities, Q equals x versus 3, 0, 0, 0, and R is 1, respectively. So the first part is to calculate minimum observable error covariance speed. That is find the optimal Karman filter in P. So the Algebraic-Riccati equation is, let's write that down. AP plus PA transpose minus P C transpose R inverse CP plus 2 equals 0. So the 0 is a 2 by 2 matrix. P is a symmetric matrix. So P11, P12, P12 and P11. Sorry, P22. Right, so let's calculate each of the quantities in the Riccati equation. So AP is P11, P12, P12 and P2. This is P12, P22 and in the first row. So since P is symmetric, PA transpose is AP transpose. This becomes P12, P22, P11, P12. Then R is a scalar, so R inverse is simply 1 in this case. So we have, so R inverse is 1. Then C transpose C is 1, 0 and 1, 0. And now we need to multiply by P on both sides of C transpose. So this is P11, P12, 1, 0, 0, 0. This becomes simply P11, 0, P12 and 0. This is P11 square. Then P11, P12, then P11, P12, and 1 second. Let me check. Well, and this is simply P12 square. So what can we observe? P22 is absent, right? So we can choose P22 after we calculate P11 and P12. Okay, so let's substitute. Um, PP. Okay. So P22 is absent in the third term, but it's present in the term, I think, AP and PA transpose. All right. So we have an equation for P2. So we have AP. This is P12, P22 plus PA transpose. Then minus P1 square. Then we have plus 3. So do is 3, 0, 0, 0. Okay, so equation 1 is 2P12 minus P11 square plus 3 equals 0. Or P11 square minus 2P12 plus 3 equals 0. So P11 is this is equation 1. Then we have P22 plus P11 minus P11 P12 equals 0. So this is 2. Then third equation is, I think, the same one because it's okay. Let's see. This is P11 plus P22 minus P11 P12 equals 0. So 2 and 3 are safe. The last equation, 2P12 plus P12 squared equals 0. So this implies that P12 is 0 or P12 is minus 2. Okay, so if P12 is 0, then this implies that P11 is plus minus under root minus 3. Okay, and if we have P11, in this case is minus 7. Okay. Let me see. Okay, so I think there is a mistake here. This is 3003, and this means that we are here, and the last equation becomes uh, 2p12. Sorry, this is wrong. So we have 2p12 minus p12 square plus 3 equals 0. Or you can write p12 square minus 2p12 minus 3 equals 0. This implies p12 is just 2 plus minus 16 by 2. This is 2 plus 4 by 2 and 2 minus 4 by 2. Okay, so choose p12 as 3. Then we get p11 equals plus minus under root 3. So note that if p12 is minus 1, then p11 would be imaginary, right? Plus minus minus 2 minus 3. This is just not possible. Feedback gain is a real quantity, right? Possible because the feedback gain k. So k is minus p inverse c r inverse is a real quantity. All right, so we have p12, p11, and I think we have p22, right? From 3, p22 is minus of p11 minus p12. So this is, let's say, under root 3, so minus under root 3, and then 1 minus 3. So this is 2 under root 3. Therefore, p is under root 3. No, this is 3, right? 3, 3, and 2 under root 3. And then we should find the feedback gain. So we need p inverse, right? Determinant of p is 2 times 3 minus 9. This is minus 3, non-zero, so p is invertible. P inverse is 1 by minus 3, 2 under root 3 and minus 3. P is minus 1 over 3. So R inverse is 1. We have P inverse and then C. C was, I think, the first state, right? 1, 0. This is 2 under root 3, 0 minus 6. So this is the optimal feedback gain. Alright, so I hope that this was clear to you. So just remember that P is a symmetric matrix, and then we can find the solution of the algebraic part equation. All right. Let's move on to the case study of the nuclear reactor. Okay, so this is part 2.1, the linear model. So we covered the theory and the numerical examples for all the three cases: the non-linear model, the linearized model, and the linear output feedback control. All right, so let's begin with the quick definition. So what does a nuclear reactor do? It's a device in which a controlled fission reaction takes place. All right, so fuel is generally uranium 235 nucleon. Or you can just say the fuel is uranium 235. So the fuel undergoes uh, fission. This results in, so it results in three quantities, right? So the first one is the fission fragments. Then it's the neutrons, free neutrons, and then the third one is other radiations. Energy of 200 MeV per fission. All right. And the output of a nuclear reactor is the electricity that it generates, right? So there are some classification of nuclear reactors. Let's look at them quickly. Uh, this condition. First is based on neutron energy. Based on the neutron energy, we have fast and thermal reactors. Fast reactors and thermal reactors. So generally in India we have thermal reactors, and I think one of the fast reactors is under construction. But I think it's operational now, so you can check that. And then classification based on the type of coolant. So, so we have sub classifications in this. We have light water, cooled reactors, then heavy water cooled reactors, gas cooled reactors, finally, liquid metal cooled reactors. Okay, so what are the main components of a nuclear reactor? So we'll see the main components. So we have the core, then there is a reflector, shield, and flux sensors. So core has a fuel moderator, then coolant, and the control rods. Then it's the reflector, shield, and finally the neutron flux sensors. Right. Now let's move on to the mathematical model of the nuclear reactor. So our objective is to model the nuclear reactor, then we'll find out that it's a nonlinear model. After that, we linearize it so that we get the state space model and then talk about its control. Alright, so there are two types of neutrons which are released, right? So once produced, and the rock neutrons, the delayed ones. Okay, so these are released within 10 to the power minus 14 seconds of the fission reaction. And then the delayed neutrons are produced due to radioactive decay. So then these have a time delay. So the effective delay constant is lambda with the unit of second inverse. And then beta is the fraction of delayed neutrons. All right, so you can see the screen. And let's just so sorry about that. I think there was an internet issue from my end. So there are two types of neutrons. First is the prompt neutrons, and then we have the delayed neutrons. So if we are talking about a fraction of the delayed neutrons, it's E. And this means that fraction of prompt neutrons would be 1 millimeter, right? Alright, so let's say that nu is the uh, total neutron yield per fission. So there are many fission reactions, and in one of the fission reactions, we are saying that nu is the total number of neutrons. Alright, so what does this mean? So prompt neutrons would be nu times 1 minus beta in a single fission reaction, and the delayed neutrons would be nu times beta. Alright, so in each fission reactions, we know how many neutrons are the prompt ones and the delayed ones. Alright, and I think there are a lot of notations which have been discussed. So please take note of all the variables which are in the description of the mathematical model of the nuclear reactor. So I'll note down the ones which we are going to use to solve the numerical examples. This is phi is the neutron flux in the reactor core. Okay, so phi at any time t is eta t times v. So eta is the neutron density, and v is the neutron speed. Then we need the time rate of change of the neutron density so that we know what's the rate of generation of the neutrons, right? In a fission reaction. So that would be eta dot of v. So this is from the lecture notes. This is k times 1 minus beta minus 1 over L times eta t plus lambda psi of t. So we have a differential equation. Okay, so we have some values k based on the parameters of the reactor model. This is nu sigma f over sigma a, and 1 upon v times sigma a is L. So I think this is the neutron multiplication factor. And L is for prompt neutron lifetime. Eta dot can also be written as rho of t minus beta over L star. So these are the variables that we're going to use times eta t plus lambda psi of t. So rho is k minus 1 by k, and this is known as reactivity. and L star is simply L over K, and this is the uh, ground neutron generation time. Alright. And in addition to this, we also have a differential equation of psi of t. So psi dot is beta over L star, beta t, sorry, minus lambda psi of t. Okay. So this is one of the equations that we're going to use. And then we have this. Alright, and then we have the transfer function, which is the output is the voltage generated due to the movement of the rods. So this is V and S. We are talking about a transfer function, so we are in the S domain upon beta S. This is output over input. This is represented by a first order system with a gain and a time constant. This is I think 10 volt per unit, and tau n is 0.17. So if we multiply 1 plus S tau n equals Kn times beta S, and then perform the uh, Laplace inverse, we get Vn dot equals minus 1 over tau n Vn plus Kn over tau n beta. So all of these are functions of time, the variables. Right, and then so Vn was is voltage, or I'll do this. Vn is the voltage associated with the neutron density. Okay, similarly, we have another VR. So this is a measurement. VR is a signal proportion to the rate of change of neutron density. And then we have again a transfer function. So this is VRS and VNS. This is KRS upon 1 plus this is again S times tau R. Okay, so let's write down all the differential equations which are associated with the nuclear model. That's the complete mathematical model. So first is, we already have seen this. This is D. So I'm going to write down eta dot. Eta dot is, I think, K rho H of T minus beta over L star times eta plus lambda psi. So let's write bracket T to show the time varying quantities. Then we have psi of T equals beta over L star eta t minus lambda psi of t. Then Vn dot is minus 1 over tau n. Vn of t plus Kn eta t. Then Vr dot, this is bar, finally H dot of t is Km times Vt. The last one is a important equation in which H is the control rod position with respect to its equilibrium. And H dot is therefore the speed of the control rod. And we have rho equals K rho H, and V is the control voltage. And Km is a constant which has been taken to be 0.004. So there is an input voltage V, and this results in the displacement of the control rod. And then by solution of these differential equations, the objective of the nuclear model is to generate electricity. Okay. So what's the order of the model? There are 5 states, right? Those states are eta, psi, Vn, Vr, and H. There are 5 states. Therefore, this is a fifth order model. And it's non-linear. So let's see. It's non-linear because I think there's a multiplication of states, right? So eta and H are multiplied in the evolution of eta, right? Might be there are no non-linear terms. All right. So what's the input? The input is the control voltage, right? Input is the control voltage of t. Alright. Now we have the nonlinear model. It's a fifth order nonlinear model. Now let's linearize it so that we can design its control. This is section 2.2. So how do you linearize a nonlinear model? We consider an equilibrium position or any position and equilibrium state and calculate the Jacobian, right? We have the differential equation. Nonlinear equations. So let's number them. This is 1, 2, and the fifth one. The nonlinear equations can be linearized around the steady state. And the procedure has been shown in the lecture slide. So I'm going to write down the linear model. Sorry, so we have not written the output. The output is Vn and Vr. So Vn and Vr are so Vr is a signal which tells us the rate of change of neutron density, and I think Vn is the voltage associated with the neutron density. So there are two outputs, one input, and 5 states. Okay. So in the linearized model, we have x dot of t equals axt plus u of t, and I write down the A, B, and C meters as for the nuclear reactor. Alright, so A is beta over L star. Now, so we have 5 states, right? So X is in R5. So what's the size of the A matrix? A would be 5 by 5, right? Alright. Then B would be, so we have 5 states and 2 inputs. It would be 5 by 2. Let me check if this is correct. Sorry, there's one input, right? Only the voltage. So this is 5 by 1. It's a column vector. C, the output, we have two quantities at output and we have 5 states. So this is going to be 2 by 5. Alright. This is 0, 0, 0, eta naught by L star. Then we have beta over L star minus lambda 0, 0, 0. Kn over tau n 0, 0, and 0. These are 3 rows. So 0, 0. This is A. Then we have B, it's a 5 by 1 column vector, right? So this is 0, 0. The input is only in the state H, right? H dot is Km times V of t. V of t is the input. So this is 0, 0, 0. And H is the last state. So, one second. Yeah, this is 0 and Km. Then C is 0, 0, 1, 0, 0, and 0, 0. R over tau R 1, 0. Alright, so if we know the values for all of these constants for a nuclear reactor, then we know the linearized model of the reactor, right? Okay. And since now we have a state space model, we can now talk about controllability, observability, and control design. Have 10. All right, so let's look at a question. So calculate the controllability matrix of the linearized model, the reactor, with the following parameters. So beta is 0.005, lambda is 0.04, L star is 10 to the power minus 4, K rho is I think 0, sorry, 20, Kr is 10 to the power 3, Km in this case is 0.001. Then we have the time constants, tau n is 0.2 seconds, and then tau r is 4 seconds, beta 0 is 2. This is a fifth order state space model. So what would be the controllability matrix C? So B, AB, A square B. Alright. So let's first write down what's A. The first quantity is minus beta over L star. So let's calculate this quantity first. So beta over L star is 5 into 10 to the power minus 3 upon 10 to the power minus 4. This is 50. So lambda is already given. Then we have K rho beta 0 over L star. And this is 20 into 2 over 10 to the power minus 4. And then I think this we have Kn over tau n. So okay, so we have to get a value for Kn also. Just a second, let me check the question. Okay, so Kn is, sorry, I didn't write it down. So K rho, Kr, Km, and Kn is 10. Right, so this is 10 over 0.2. This is 50. We also need 1 over tau n. This is 1 over 0.2. This is 5. We need 1 by tau r. So this is 1 by 4, 0.25. So this is second inverse, right? Then Kr over tau r squared. This is 10 to the power 3 divided by 60. Let's see. Uh, this is going to be okay. So let me know if there are any calculation mistakes. So the matrix A is minus beta over L star. This is minus 50. Then lambda 0.04, 0, and k rho eta naught over L star. This is 4 into 10 to the power 5. Alright, then we have beta over L star again. This is 50 minus lambda kn over tau n. This is 50, 0 minus 1 over tau n, 0, 0. We have minus kr over tau r squared, which is minus 62.5, minus 1 over tau r, minus 0.25, and then 0. The last row of the A matrix is always 0. So note that down. Let's make a mark. The last row is 0. And the first row is simply 0, 0, 1, 0, 0, right? So it's the third state. Let's see what this third state is. This is Vn. Observe that the non-zero entry Kn is in the last row. The only non-zero entry is in the last row. Okay. So B is therefore 1, 2, let me write down this as a row vector. This is 1, 2, 3, 4, and Kn. Kn is already given. This is 10 to the power minus 3 transpose. Now see, first row is the state Vn, and Vn is the third state. 0, 0, 1, 0, 0. And we have 0, 0, kr over tau 1. So let's complete that. Kr over tau 1, 2.25 into the power 3. So it's 250 and 0. Okay, so let's find out AB. Okay, so observe that the only non-zero entry B is the last entry, right? So if you multiply by A, this means that we are extracting the last column of it. So I write this down. Or you can just observe, right? Let's say A is in 2 by 2 matrix. This is A1, A2, A3, A4. And B is simply 0, B. So what's AB? This is 0, B. So this is B times A2, B times A4. This is the last entry times the last column of it. So AB is Km times the last column of it. This is 4 into 10 to the power 5, 0, AM is 10 to the power minus 3. So this means we have 400 and then zeros. We need a square b, which is a times ab. Um, okay, so now it's the first column, right? So let's see if we can do this. So let's say we have A1, A2, A3, A4 for a second order system. We have B0, B times A1 and B times A3. So it's the first column of A times B. So this is 400 times the first column of A. This is minus 50, 50, and then two zeros. So this becomes 10 to the power 3 and 20 into 10 to the power 3 and 0, 0. Or you can just write as minus 2 into 10 to the power 4. I'll write this down as a row vector. It says minus 2 into 10 to the power 4. 2 into 10 to the power 4, 0, 0, transpose. Alright. And now we have a general column vector, so we have to multiply A cube B, right? So A with A square B. So A cube B is A times A square B. So let's write down the matrix. We have 0 0.04, 0, 0, 4 into 10 to the power 5. And 50, and then 3 zeros. We have 50, 0, minus 5, 0, 0. And 0, 0, minus 0 0.25, and 0. The last row of A is always 0. Then A squared B is minus 2 into 10 to the power 4. Okay, so the last, this is 5 by 5 and this is 5 by 1. So it's going to be a column vector with 5 elements and the last element is going to be 0 because the last row of A is 0. Okay, so then we have minus 50, so plus 50 into 2 into 10 to the power 4 plus 0 0.04 into 2 into 10 to the power 4 and then zeros. Then we have minus into 2 into 10 to the power 4. Okay, then we have minus 50 and minus 5 into 2 into 10 to the power 4. And then this is minus 62.5 into 2 into 10 to the power 4. Let me know if there are any calculation issues. And I can use a Z. Okay, so the first is so 10 into 10 to the power 5, right? So it's 10 to the power 6. Then it's plus 8 into 10 to the power 3. Mm, okay. Then we have minus 10 to the power 6 plus 8 into 10 to the power 2. So what's this? It's 0.5 into 2. So this is 125. Minus 125 into 10 to the power 5. Non-zero. So this becomes 10 to the power 6 plus um, okay, so this is going to be right. So this is 1.0008. 1.0008 into 10 to the power 6. Then this is sorry, this is wrong. So this is minus 1 plus 0.00. Okay, so let's make some as a approximations. It is approximately equal to 10 to the power 6, 10 to the power minus 10 to the power 6. Then we can add these two quantities, right? 10 to the power 6 and 5 are comparable. So this is minus 1.1, 10 to the power 6. This is a big quantity, so 125 into 10 to the power 4 and 0. Alright. And now we need to calculate a to the power 4. Okay, so this is a times a cube b. And let's rewrite a. This is minus 50, 0.04. And then the last row is 0. So this multiplied by a cube b, this is 10 to the power 6. Alright, so the first entry is minus 5 into 10 to the power 7 minus 10 to the power 4. That's it, right? Then we have 5 into 10 to the power 7 minus 10 sorry, this is 4 into 10 to the power 4. Then we have 5 into 10 to the power 7 and plus 5.5. Sorry, this is into 10 to the power 6. Okay, then 0, 0. And then this is 0. Okay, so the controllability matrix would be 5 by 1 matrix, right? So it would be B first. This would be 0, 0, 0, and Km. Km is 10 to the power minus 3. We will have A square B, sorry, AB, and A square B, A cube B, power 4B. Okay. And last terms are going to be 0. We have already completed AB. This is 400. The first one. Alright, then A square B, so minus 2 and 0. We have A cube. So this is 10 to the power 6. Have the quantity, the elements for e to the power 4b. So I think you can, for the moment, let's just write them as some alphas. Let's say this is A1. So this is so these are 5 columns and 5 rows. Okay. So we need to find the determinant of the controllability matrix because it's a square matrix and this will determine the rank. So determinant is 0, then the controllability matrix is not for rank. So determinant of C. So let's expand the determinant along the first column. It would just have the entry for 10 to the power minus 3, right? So 10 to the power minus 3 and the determinant of 400. Okay. And now let's expand along the first column again because the only non-zero entry is 400. So 10 to the power minus 3 into 400. We have to expand the determinant of this 3 by 3 matrix. This is 10 to the power minus 3. So this is 4 into 10 to the power 2 into 10 to the power minus 3. This is 0.4 times 4 minus A3 times 125 into 10 to the power 4. We should expand along the first column because it has two non-zero entries instead of 3, right? This will be minus 2 into 10 to the power 4, 10.6 A4, minus 125 into 10 to the power 4, A2. Okay, so let's see if we can collect some terms. This is A2 into 10 to the power 4 A2, sorry, A4, into 10 to the power 6, and then we have minus 1.1 and minus 1. And minus A3 into 125 into 10 to the power 4, and minus 125 A2. So 0.4 into 10 to the power 4 will be 4 into 10 to the power 3 into A4. So I think this is minus 1.1. This is minus 2.1. You can multiply this by 2. This is minus 4.2. A4 into 10 to the power 6. And we have minus A3. So 125 A3 minus 125 A2. So this becomes A4 into 10 to the power 6 minus 125 A2 plus A3. So let's find out A2 plus A3. This is A2 plus A3 equals. This is 10 to the power 8. Let's do that first. So this is 5 point. This is into 10 to the power 3 divided by 10 to the power 3. 0.004 into 10 to the power. So this is minus. So this is 5 minus 0.004. So let's calculate this. I'm not sure if we should approximate this at 5. Let's do this. So this is approximately equal to 5 into 10 to the power 7. Then we have plus 5.55 into 10 to the power 7. So let me know if the calculations are correct. This is So we have 10.55 into 10 to the power 7. So let's substitute A4 here if we also have that. A4 is this is 10 to the power 2 over 2. I have to multiply 62.5 and 1.1 in this case. Let's say this is 62 point. So A4 is approximately 62.5 into 1.1 into 10 to the power 6. Ten point five five into 10 to the power 7. Okay, so now we have to multiply by 10 to the power 4. So 5 over 5, right? So this is going to be approximately minus 4 into 10 to the power 3 into 4.2 into 62.5 into 10 to the power 12, which is non-zero. This implies that the rank of the controllability matrix is 5, which implies that the pair AB is controllable. Alright. So now we can also test for observability. The observability matrix would be C, CA square, and you can check the rank of C to comment on the observability of the system. You can also use the hottest test. Alright. Now let's move on to the linear output feedback control design. So if you have any doubts, now let me know. I'm going to move on to the next section. Alright, so the control is U equals G of Y. So some feedback gain G times the output. And Y is C of X. So this is simply Cx. So the closed loop system is AX plus BGCX. So this is the closed loop system. Alright. So what's the dimension of C? We have 5 states and 2 outputs. So C is going to be 5 by 2 and B is 5, 2 by 5. Let me see. No, sorry. So C is 2 rows and 5 columns. B is 5 by 1. So BGC, the multiplication of these three matrices, has to be added with A, right? A is 5 by 5. So this should be a 5 by 5 matrix. So what's the dimension of G? So the number of rows here should be equal to the number of columns of G, and they should also be the same. The number of columns of B should be equal to the number of rows of G for correct matrix multiplication. So G is 1 by 2. Uh, Let me see if this is it. Yeah. So it's 1 row, 2 columns. Let's say this is G1 and G2. This is N1. Okay, so let's find out what is. So let me write down the question. This is question 2. So for the parameters given in question 1, from G1 and G2. So let's say 1 and G2 is 3. Find out the four locations. Obtained by applying the output feedback control. So let's first find out BCG. B is so the only non-zero entries in the last column. So we have 1, 2, 3, 4, and KM was 0.00. So it's 10 to the power minus 3. So it says BGC. Then we have G1, G2 times C. So the first row of C is the first output, and the first output is the third state. This is 0, 0, 1, 0, 0. Then we have 0, 0. There's a non-zero entry here. This is we are over tau r. We have already, yeah, this is 250. This 1, 0, right? Let me check. 1, 0. So this is 0, 0. This is 1. This is 3. And this is 0, 0, 1, 0, 0. The first is going to be 0, right? The only non-zero entry is going to be the last row. 0. 10 to the power minus 3 plus 3 into 250 into 10 to the power minus 3. Then 3 into 10 to the power minus 3 and 0. This is 751 into 10 to the power minus 3. Let's just write this down ourselves. Consideration. Okay, and now we add A and B, G, C. So observe that there are only two non-zero entries, right? So we'll just add the two non-zero entries to the corresponding entries of A. So let's say I have to go up. And the last row of A is 0. So we'll just have to add those two non-zero entries in these places, right? So let's write this down. Minus 50.04 and this is 0, 0 and uh, 5 into 10 to the power 4 into 10 to the power 5. Then it's 50 and 0.04. We have 50, 0, minus 5. Then it's 0, 0. So it's minus 62.5 and 0.8. And the last row of A is 0. And we have added those two elements. This is 0, 0, 751 into 10 to the power minus 3 and 0. Okay, so pole locations of the closed loop system. Are the eigenvalues of A plus B, G, C. Okay, so what's the characteristic polynomial? So let's just write this one. So this is determinant of A plus BGC minus lambda r equals 0. So we have to solve this characteristic equation. Okay, so let's write this down, which is minus 50 minus lambda 0.04 minus. So we'll just subtract lambda from the entries on the main diagonal. This is minus 5 minus lambda and then minus lambda. 50. No, I think I missed out. Yeah, sorry. This is 50 50 and 0, 0. This is 0, 0, 0. 4 into 10 to the power 5, 0, 0, and 0. So the determinant of this, right? Okay, let's see which row or column has the least number of elements. It's column 2 or column 5, right? So let's expand along column, the last one. So expanding along column 5. Okay, so this is the going to be 4 into 10 to the power 5. Zero. And then this is minus lambda times. Alright. So then we can expand along the second column. It's 4 into 10 to the power 5 into 0.04 minus lambda. This is 50 minus 5 minus lambda 0. Okay, and for the next 20, we can expand along the last column. So this is minus lambda. This is a 4 by 4 matrix, right? So this is times minus 0.25 minus lambda. We can now expand along this first column and the last term. This is 4 into 10 to the power 5 into 0.04 minus lambda into 50 times sorry, this is multiplication. This is so that's 50 into 0.84. This is simply 2 by minus 2. Okay, so let's see. Let's solve out this characteristic equation. It should be 5, right? Because A is a 5 by 5 matrix. So this is lambda square. Let me check. Yeah, you can observe from here, right? This would mean lambda square, and this would be lambda. So this would give a fifth order equation in lambda. So you get something like lambda to the power 5 plus some coefficient alpha 4 lambda 4. Okay, and then we can find out the eigenvalues. Alright, so that's it. These are all of the questions. If you have any doubts regarding the assignment or the tutorial, you can ask me now. If you don't have any questions, then you are free to leave. Yeah. Not known to find the lambda value. Last step. Yeah. So, solving this equation, getting the roots of this equation means finding the eigenvalues of the closed loop matrix A plus BGC. I think all of the numerical questions that we have done in all of the tutorials. So it starts from state transition matrix, um, controllability, observability, and then I think it was I have to check. One second. So, yeah, so finding the solution of the state space system that requires the computation of state transition matrix. And then you have to remember the properties of the state transition matrix to solve a few questions. Then I think it's controllability, observability, and if you do not have a completely controllable observable system, then you have a smaller subsystem, right? Which is controllable and observable. So you can design the controller for that. And then I think it's okay, yeah. Then it's a Lyapunov stability, right? So you have a non-linear system, and then we assume a Lyapunov function to comment on the stability of the origin. So that is important. Then it's marginal stability and Lebo stability. So this is the non-linear one. After that, we had LQR design, right? So LQR design for LTI systems. Then in I think controllability, we had the pole placement design. This was finding out the eigenvalues of the closed loop matrix A minus B2. And similarly, the observer gain design, right? So that was A minus LC, finding the eigenvalues of A minus LC. And then after that, we had LQR and then the estimation problem, finding out the error covariance matrix P and the Kalman gain K. And finally, we have the nuclear reactor. Can you find? Thank you. All right, if you have no questions, it's fine. You are free to leave. Right. Yeah.